Good day, everyone. I, together with OMAIMA D. BOCARI and John Michael D. Cortez, are going to discuss about double integrals over general regions. So here are the objectives. At the end of the discussion, students should be able to first integrate two variables functions over a general region D in real numbers square. Second, compute areas of regions between curves using double integrals. And lastly, choose which order to do the integration when computing a double integral over a general region. So first, double integrals are a way to integrate over a two-dimensional area. In the last lesson, we learned how to do the double integral of a function of two variables over a rectangular region. Now, we will study how to integrate two variable functions over a general region D in real numbers square. To demonstrate how this works, we will start with an example. Integrate the function f of x and y equals 6xy squared over the triangular region D with vertices 0 and 0, 1 and 0, and 1 and 2. Figure 1 shows the triangular region D. We first notice that region D can be described as the region enclosed by the curves y equals 0, x equals 1, and y equals 2x. One way to write this region is D equals x and y divides x greater than or equal to 0 and less than or equal to 1 and y greater than or equal to 0 and less than or equal to 2x. In other words, we vary x between 0 and 1 for every fixed value of x. We vary y from 0 to 2x. The iterated integral would be written as double integrals over region D of 6x raised to 2 dA equals double integrals from 1 to 0 and 2x to 0 of 6xy raised to 2 dy dx. Notice the order in which the integrals are written with the x integral on the outside and the y integral on the inside. Unlike rectangular regions, we cannot arbitrarily switch the order of double integrals when D is a non-rectangular region. When doing any double integral, the outer integral must always have constant bounds, but the bounds on the inner integral may be functions of the outer variable. Doing the inner integral with respect to y gives us the integral from 2x to 0 of 6xy squared dy equals 2xy cubed integrates from 0 to 2x equals 2x times 2x cubed minus 0 cubed equals 16x raised to 4. Plugging this into the outer integral, we get integral from 1 to 0 of 16x raised to 4 dx equals 16 over 5 integrates from 0 to 1 equals 16 over 15. We could also have done this integral in the other order with x as the inner variable, but it would require some modification since the outer integral bounds must be constants. The region D can also be written as region D equals x and y divides y greater than or equal to 0, but less than or equal to 2 and y divides x greater than or equal to 2 but less than or equal to 1. In other words, we vary y between 0 and 2 for every fixed value of y. we vary x from y divides 2 to 1. The iterated integral in this case would be written as double integral over region D of 6xy squared dA equals double integral from 2 to 0 and from 1 to y divides 2 of 6x squared dx dy. This shows that we can switch the order of integration for double integrals over general regions, so long as take care to describe the region in a way where the outer integral bounds are constant. Doing the inner integral with respect to x gives us integral from 1 to y divides 2 of 6xy squared dx equals 3x squared y squared integrates from y divide 2 to 1 equals 3y squared of 1 squared minus y divide 2 squared equals 3y squared minus 3 divide 4 y raised to 4. Plugging this into the outer integral, we get integral from 2 to 0 of 3y squared minus 3 divide 4y raised to 4 dy equals y cubed minus 3 divide 20y raised to 5 integrates from y equals 2 to y equals 0 equals 2 cubed minus 3 divide 20 times 20 times 2 raised to 5 equals 8 minus 24 over 5 equals 16 over 5, which is the same answer we got the first time in the example.
For our example 1.1, describe the region of integration and switch the order of integration for the iterated integral. This figure here, which is figure 2, shows the region bounded by y equals x and y equals x squared. So for our solution, the region D being integrated over is D equals the quantity of x and y where 0 is less than or equal to x, less than or equal to 1, and x squared is less than or equal to y, less than or equal to x, which is the region bounded by the curves y equals x squared and y equals x. This region can also be written as D equals quantity of x and y where 0 is less than or equal to y, less than or equal to 1, and y is less than or equal to x, less than or equal to square root of y. So switching the order of integration results in the integral of from 0 to 1, then the integral of from x squared to x of the function x and y dy dx equals to the integral from 0 to 1, the integral y from y to square root of y function of x and y dx dy. Gets? Nice. For our next slide, areas of general regions. Since dA represents an infinitesimal area of the region D, we can compute the area of D by adding up all of these infinitesimal areas with an integral, double integral D, dA equals to A of D. Example 1.2 here states, using a double integral to find the area of the region D bounded by the function of g of x equals x squared and h of x equals 2 minus x squared. Figure 3 shows the two functions. Okay? So for the solution, g of x equals h of x. So we substitute here x squared equals 2 minus x squared. Then 2x squared equals 2, where x equals to positive or negative 1. Since we divide both sides by 2, then we cancel out 2, then we square root both sides to cancel the squared of the x, which give us positive and negative values of 1. Since 2 minus x squared is greater than or equal to x squared, when negative 1 is less than or equal to x, less than or equal to 1, the region D is written as such that D equals x and y, where negative 1 is less than or equal to x, less than or equal to 1, and x squared is less than or equal to y, less than or equal to 2 minus x squared. So the area of the region is double integral d dA equals the integral from negative 1 to 1, integral from x squared to 2 minus x squared dy over dy dx equals, from here, you need to separate h, which give us the value of 8 over 3. For this, the average value of the function of x and y over d is double integral 1 over a of d, double integral of d, function of x and y multiplied by dA, where a of d is the area of d. Since a of d equals double integral from d of a, we can write the average value as that one right there. That is the formula.
Okay, so let's now proceed to the region types or types of region. So there are two types of region, namely type 1 and type 2. So let us first define type 1 region. We define a type 1 region as one that is stated as region of D is equal to the set of x and y such that x is greater than or equal to a but less than or equal to b, and y is greater than or equal to the function g of x but less than or equal to the function of h of x, where h of x is greater than or equal to g of x for all x is an element of a and b. For regions of this type, a double integral should be done in the order. So this is the order of the double integral of type 1 region. So we read this as the double integral over the region D of the function f of x dA is equal to the integration from a to b and integration from the function g of x to h of x of the function x and y dy dx. So here is how the type 1 looks like. These two vertical boundaries here are the constant, which is the x, where x is equal to a and b. And these two top boundaries here, these curved boundaries here, are the functions of x. So this shaded part here is the region, or the region D. So this is the example of a type 1 region. So next, let's proceed to the type 2 region. Type 2 region is one that is stated as the region of D, which is equal to the set of x and y, such that y is greater than or equal to c, but less than or equal to d. And x is greater than or equal to the function g of y, but less than or equal to the function of h of y, where h of y is greater than or equal to the function g of y for all y is an element of c and d. For region of this type, a double integral should be done in the order. So, the double integral over the region of D of the function x and y dA is equal to the integration of integration c from c to d and the integration of the functions from g of y to h of y of the function x and y dx dy. So this is the how the type 2 region looks like. This is the other way of type 1. So this, the type 1, the constant there is the vertical line. But in the type 2, the constant here is this horizontal line, boundaries. These two horizontal lines here are the constant y, where y is equal to c and d. And these two boundaries here are the functions of y. Yes, the functions of y, and these are, this shaded part here is the region of t. So, in this order, we first integrate the inner part, which is the functions of g of y to h of y, of the function x and y with respect to x. And next, after we have integrated the inner integral, we then integrate the outer, which is the integration from c to d. So same as to the type 1 region, we first integrate the inner, which is the integration from integral from g of x to h of x of the function x and y with respect to y. And then next is the outer. After getting the integral of the inner integration, we have to get the constant of the integration, which is the integral from a to b. So let's have an example. Integrate the function x and y is equal to xy over the region bounded by y, which is equal to the square root of x, and y is equal to the square root of 2 minus x, and y is equal to 0. Since 2 minus x squared is greater than or equal to x squared for all x in the region D, the region D is written as the region D is equal to the set of x and y such that y is greater than or equal to 0 but less than or equal to 1, and x is greater than or equal to y squared but less than or equal to 2 minus y squared. And the double integral will be like this one here. So we read this as the double integral over the region of D of the function x and y dA is equal to the integration from 0 to 1 and the integral y squared to 2 minus y squared x y dx dy. In integrating these two, we have to integrate first the functions, which is this one, y squared and 2 minus y squared. And then after that, we have to integrate the constant, which is the integration of from 0 to 1. So, doing the inner integral from y squared to 2 minus y squared x y dx is equal to 1/2 x squared y. Integration x is equal to y squared and x is equal to 2 minus y squared, which is equal to 1/2 1 over 2y. The quantity of 2 minus y squared squared minus y squared is equal to, so we will distribute the exponent here, the outside exponent, and then this will look like this again. 1 over 2y multiplied to 4 minus 4y squared plus y to the 4th power minus y raised to 4 is equal to 2y minus 2y cubed. plugging this in the outer integral, which is the integral from 0 to 1, and then we will plug this one. The result of the inner integral, which is 2y minus 2y cubed with respect to y, is equal to y squared minus 1 over 2y raised to the raised to 4, where y is equal to 0 and y is equal to 1. And this will be equal to 1 minus 1 over 2, and 1 minus 1 half is equal to 1 half. So this will, the region looks like. The type 2 region bounded by y is equal to square root of x, and y is equal to square root of 2 minus x, and y is equal to 0. This shaded part here is the shaded part here is the region of D. We're looking for the region D. So this part here is the region of D. Shaded region is the region of D. And this is how it looks like. So another one is D sub 1 is equal to the set of x and y, where x is greater than or equal to 0 but less than or equal to 1, and y is greater than or equal to 0 but less than or equal to the square root of x. And d sub 2 is equal to the set of x and y, where x is greater than or equal to 1 but less than or equal to 2. And y is greater than or equal to 0 but less than or equal to the square root of 2 minus x. So this splitting a type 2 region into two type 1 region. So this is the type 1 region, this part here, and this is the type 2 region here. Since D is equal to D sub 1, which is the union set of D sub 2, the integral can be computed as the double integral over the region of D of the function x and y dA is equal to the double integral over the region of D sub 1 of the function x and y dA plus the double integral over the region D sub 2 of the function x and y dA is equal to the integral from 0 to 1 and integration from 0 to square root of x of the function xy dy dx plus the integration from 1 to 2 and the integration from 0 to square root of 2 minus x of the function xy dy dx. So we will just add the d sub 1 and the integration of d sub 1 and the integration of d sub 2, and that will be equal to the double integration of over the d region. So that's it. So we have the activity. For your activity, write your answer on a clean sheet of paper. Find the average value of the function. First is find the average value of the function f of x, which is equal to 2xy over the region D bounded by x is equal to 0, y is equal to 1, and y is equal to x squared. And next is determine the easiest order to do the integral of double integral over the region of D y squared e raised to x and y dA, where D is the region bounded by y, which is equal to x, y is equal to 4, and x is equal to 0. So you can submit your activity before the presentation of the next reporter or the next group. So you have plenty time to answer this activity. So that's all. And thank you for listening.